I had an idea after I had an email exchange with a student last night, and I thought, because I know with Wi-Fi issues and whatnot, it may take a second to scan the code, so I thought, why don't I put the QR code on the attendance slide, because I end up taking a minute and going through the slide, and so that might make it a little easier for folks that are still finding your seats and whatnot. Okay, I have here that homework 2.3 is graded and 2.4 is being graded. 2.4 is actually done. I just turned that on just before class. However, I know there's a couple of you for 2.3 or 2.4 that the grade is still lingering, and I think what had happened is maybe you had done, it had either been that those were still instances where students had done the wrong problem in the textbook, or the TH just wanted me to take a look at it. So I will get to those today. So if you look and your 2.3 and 2.4 are still outstanding, then it'll probably be taken care of by the end of business today. 2.5 is being graded and 2.6 is due today. Okay. Now I'm going to assign 2.7 that's due Friday, and that's going to be the last homework that's due before the first exam. Okay. What's going to happen is, so today 2.6 is due, on Friday 2.7 is due, and then Monday and Wednesday we don't have any incoming homework, because Monday and Wednesday are our exam review and our first celebration. I will also tell you that today is the last topic on exam 1. So what we cover on Friday is going to affect your homework assignment that's due after the exam, but what we cover on Friday is not going to be on exam 1. So this is it, okay? Today's lecture is the last topic that you will be responsible for on exam 1. Sound good? All right, so everybody good on the schedule. One other thing I'll say, I'll go ahead and say it now while it's on my mind, about exam 1 review. So the way that the exam review is going to work is I'm going to come in and I'm going to tell you the overall format of the exam. You know, the types of questions, what to expect. I will go ahead and tell you the exam is going to be closed book and closed notes, but I'm going to let you bring in a self-made formula sheet that you can, for the most part, put whatever you want on there. But I'll talk about the details of that on Monday. But what I'll do is I'll give you sort of a rough overview of the exam, both the format and the topics, and then I kind of shut up and I let you ask whatever you want. So most of Monday is really you. So I guess my point is, when you come in Monday, if you have any lingering questions about a homework assignment or a topic, or there's something you didn't understand, come prepared for questions, because chances are if you have a question, there's somebody else that has the same question, and we can have a really interactive discussion, and it can be valuable. I want you to come into the exam. I don't want it to be stressful. I genuinely, I'm not trying to trick you or come up with these crazy curveballs on the exam. I want it to be as straightforward as possible. Sound good? All right. Okay, so we are going to sort of end our discussion of statics of particles today by looking at equilibrium in 3D. Okay, so up until now, we discussed some similarities between 2D and 3D, and what we were focused on last time was, I would argue, what we were focused on were these three boxes up here, and I guess maybe this one down here, but what we were focused on is adding vectors together. So we were describing vectors in 3 dimensions, and then we had a system where there were a bunch of vectors, and then we added those vectors up. Okay. Now what I want to do is I want to assess static equilibrium. So in other words, I have a bunch of forces all meeting at a common point, and I'm going to have unknowns at that in that system. And so I need to determine those unknown forces in order to achieve equilibrium. Now, static equilibrium in 3D, I do not believe it is any more difficult than static equilibrium in 2D, but the problems can be longer. There's more components, ends up being a little bit more math just with the vector description, but the process is the same. Define your vectors, add them up, take each of our 3 equations, each of the columns of values, develop 3 equations and 3 unknowns, simultaneous equation solution, go home. Not too bad. So I would say make sure you're comfortable with your calculator today. If you're using a Casio, we've been using mode 1. Today we're going to be using mode 2 because we got a 3x3 system today instead of a 2x2 system. Sound good? So actually the bulk of today's lecture is going to be focused on this example problem. Today's example is brought to you by the movie Up. We have, gotta have a joke a little bit early in the morning. So I have a balloon that is exerting an upward force of 800 newtons, and it is being held down by these three cables that are oriented on the dimensions shown. And what I want to determine is the tension in these cables. I think it's a pretty easy problem to understand conceptually, but it's going to take a little bit of math to get from point A to point B. I think you'll find that as we start going through the process, it will be very familiar. It may be a little longer than what we've done before, but it will be very familiar and I think hopefully very rote. So let me go ahead and pull up the notebook. I have this example already defined in the notebook here as well. So let me make this a little bit bigger. All right, so we have a balloon that's held in place by the three cables shown, and we need to determine the tension in each of these cables. So I think what we could do is just make sure that we're all on the same page, in terms of a free body diagram. And I will try and write a little larger this time. So if there's anything that is too small on my handwriting, please tell me. Okay, so our free body diagram is going to be focused around point A, and I think that's pretty, easy to understand at this point. That we have, this point that has how many forces going through it? Well, we have the force in each of these three cables, and also the upward force from the balloon. So there's 4 forces being applied at this point A. So we'll call, this point A, and we'll say that we have the upward force from the balloon. I think I'm going to call that F sub B, just F for the balloon. Is everybody can read that? Is that legible? Okay. And then we're going to have 3 unknown forces. And I'm just going to label those, tension, AB, AC, AD. So maybe we'll call that like that. Like that. Like that. So we'll call this tension AB, tension AC, tension AD. And those are the unknowns. Those are the 3 unknown forces that we're trying to determine. The other thing I would just make sure that we're all clear on is that the magnitude of, let's go ahead and write this. I'll say note. What is the magnitude of that force? The magnitude of vector FB? 800 newtons, right? Okay. And notice how the balloon force is going to act upwards. And I think that makes sense just from a physics standpoint. If I'm holding a balloon in my hands, the balloon is pulling upwards. So just right off the bat, if I were to describe FB as an IJK vector, what would be the equation for FB? I'm just curious. Basically just 800J, because there's 0 I, 0 K, but the 800 Newton force acts in the Y direction, so it is 800 J, and it's positive 800 J because it's acting upward along the Y axis. If it was acting downward, it would be negative 800 J. All right, does that make sense? Okay, now so FB I think is very easy to describe. The other 3 are going to take a little bit of work. Okay, so I'm going to scroll down a little bit. I want to make sure I've got the balloon kind of in view, okay? And let's start off with our distance vectors. Actually, let me write that a little bit bigger. So, like before, when we have forces in 3 dimensions, what we found last time is it was easier to start off by defining the distance vectors, then divide those vectors by their magnitudes to get unit vectors, then multiply those unit vectors by the magnitudes to get the force vectors. So we kind of go a little bit of a roundabout way to describe our force vectors, but it's also a lot more systematic. So we're going to have AB equals something times I plus something times J plus something times K. And what I'm going to do is I'm going to copy that. Oh, let's see. Is that going to like me? I won't be lazy. I'll just write it out. So we're going to have AC and then AD. Okay. So our goal is to use our coordinate system to describe these vectors, these distance vectors. And so I just want to take each vector one at a time and take each axis one at a time. So let's start off with vector AB. Okay. So here's vector AB. Now let's be sure. Okay. So in this problem, the axes have already been labeled for us. So this is the x-axis. The y goes up. Z goes this way. All right, so let's start off with AB. What's our x value going to be? What's this value going to be right here? Negative 4.2. Okay, that's exactly right. So negative 4.2 meters. Does everybody see that? Okay, what about the y component? Say it again. Okay, is it 5.6 or is it negative 5.6? Negative because we're going down, right? Because we're going from A to B. I want to make sure that, okay, so one thing I will say for the notation, when it says AB, we're going from A to B. So I usually like to go like literally, even if I have to use my hands, I'll go from A to B. That notation is actually going to be, and that the way that we describe that vector is going to be very important when we get to our exam 2 material and we start looking at moments. So yeah. But this is really important. I want to make sure everybody's clear on this. Everybody okay here? All right, so this is negative 5.6. What about the z vector? What is this component going to be? Okay, I heard say, what was it? 0. That's 100% right. It doesn't move along the z-axis at all from A to B. So this is 0. I'll tell you what, we could probably make a pretty easy observation. What are all of these components going to be? Negative 5.6, because we're going from the balloon to the ground for every one of them. So all of these are going to be negative 5.6. All right. All right, now let's deal with AC. So AC is this vector right here. So from A to C along the x-axis, how far do we go? 2.4. I heard a couple people say that. All right. What about the z direction? I think we're actually going to have a value in the z direction this time. What's it going to be? 4.2. All right. Any questions? All right. Last vector, AD. AD along the x direction, what's that going to be? 0. And then along the along the x direction, 0. Along the z direction, what's that going to be? Negative 3.3. 100% right. Okay. Anybody have any questions on this so far? Okay. I think this is the hardest part of this entire problem. We got a lot of math we're going to do past this, but once you have these 3 vectors, you are good to go. Sound good? Okay, so I have distance vectors. What's my next step? What do I do to these distance vectors? So, okay, IJK notation, so they're in IJK, but if I have distance vectors, I ultimately want force vectors. How do I turn these to force vectors? What do I do to these distance vectors? Divide them by their own magnitude, right? So I need to compute their magnitudes, right? I need to know their magnitude. So let's do that. So now we've got our distance vectors. Let's compute our unit vectors. And our unit vectors, the formula is we take the vector and we divide it by its own magnitude. So let's see if we can do this off to the side real quick. Can somebody tell me, okay, so what is the magnitude of vector AB? Can somebody do that calculation off to the side and tell me what that is? How do we determine the magnitude of that vector? Now you said 7. How did you do that? What formula? You just use the Pythagorean theorem. You're just using it for 3 terms instead of 2. So vector AB, the magnitude is 7 meters. Do I have a second on that? Is it okay if I just kind of do that instead of actually going through and doing the calc? I mean, I could show you. All we did is we said, negative 4.2 squared plus negative 5.6 squared plus 0 squared, and we just took the square root and we get 7. So that's all we did there. Is that okay? All right. Okay. So, therefore, that unit vector, so I'm going to take each of these terms and divide it by 7. What is 4.2 divided by 7? Oh, I hear the familiar slides of the lids on Casio FX115 ES Pluses or similar scientific calculators. This is 0.6, and this one's going to be 0.8, I think it is. Okay, yeah, 0.8. So therefore, this is negative 0.6I plus negative 0.8J plus 0K. Notice how I did not write any units inside this unit vector because unit vectors are dimensionless. They have no units. We have divided out the units by taking this and dividing it by its own magnitude. And that happens with any unit vector. Okay? So now let's do the magnitude for AC. Anybody got a magnitude for AC? 7.4. Do I have a second?
Yeah.
Okay. Now I'll go ahead and tell you this unit vector, it's a little messy. Like the terms do not come out as neat and pretty as we do in this one. I'll go ahead and write this one out. I want to see if I'm getting the right values. I'm getting 0.3243I. I'm getting negative 0.7568J, and I'm getting 0.5676K. Are you getting the same thing I'm getting? Okay, yeah, that one's a little messier, I would say. It's not as neat and pretty. All right, I'll have you help me with the last one, though. Okay, so AD, what's the magnitude of AD going to be?
6.5.
I heard a bunch of people say that, so I know it's seconded. All right, so lambda AD, so I know this is 0. What about this component? The J component. So what's that divided by 6.5?
Wait,
8615, something like that? Is that positive or negative? Negative, right? I can do better than that. All right. and then the k vector, so that divided by that, what do we get? I think this one's -2. Negative as well, not -2. Don't be shy. What does the Casio FX115ES plus or similar scientific calculator yield?
-0.5077.
Do I have a second? All right. There we go. So far, so good, right? Not too bad. So now what we're going to do is we're going to describe our force vectors. So I know this is going to feel like we're writing this all over again, and in some instances that's kind of going to be the case. But I think it's valuable to do this to ensure that you get your expressions correct at the very end. So force vectors, and again, in order to define that force vector, we take the magnitude of the force and we define or multiply it by its corresponding unit vector. So this problem, according to our free body diagram, has 4 forces: TAB, TAC, TAD, and then the balloon force. So let me scroll down a little bit. All right. So therefore, TAB is the following. So we have -0.6 TAB times I plus -0.8 TAB times J plus 0 K. And if you notice, I'm kind of spacing this out. I'm kind of yielding a lot of space between these parentheses, because ultimately what I do when I apply the equations of equilibrium is I'm going to sum columns. And so I want to make sure that all of my vectors are organized appropriately. So TAC is, okay, now how are we going to do that? We're going to say 0.3243 TAB plus, TAC. That doesn't count on my 7 mistake counter because I caught it. Again, Marshall policy says I'm allowed 7 mistakes per semester. But again, I'm the one that counts the mistakes, so I know it's a corrupt system. And this is 0.5676 TAC. Then AD is 0 here, and then plus, so we have 8615 times TAD, but negative, so negative 0.8615 TAD, bless you, plus, and then negative 0.5077 TAD. Okay. But is that all our forces? No, we have one more, right? We have our balloon force, which is going to be something times I plus something times J plus something times K. But didn't we already figure that out? Didn't we already define the balloon force vector? What was it? In the K direction, or which one was it? Yeah, this one was along Y, so it's the J direction, right? So yeah. All right, 0, 800 newtons, bless you. And that's 0. Okay. Sound good? Now, again, the reason for writing it in this fashion and sort of writing it again is because now it makes the description of my equations of equilibrium so much more easy to do, okay? So what I can do is I can say, okay, this column, if I were to sum up everything in this box, I would be summing up the forces in the x direction. And the sum of those forces must be equal to 0. right? So now that it's written in a neat, tidy, organized fashion, that's going to be set equal to 0. Now, one thing I'm going to add to this, and it might sound a bit superfluous, but I'm going to do it for a very specific reason. I'm going to go ahead and include a 0 TAD, and up here I'm going to include a 0 TAB, okay? And the reason for that is, let me rewrite that, 0 TAB. The reason for doing that is that when I fill out my my matrix solution, I want to make sure that I'm accounting for all of the respective terms. Okay. So likewise, when I sum everything up in this box, I'm going to get the sum of the forces in the y direction equals 0. And finally, for this box, this is going to be the sum of the forces in the z direction. So I'm going to have 3 equations, 3 unknowns, and should be pretty straightforward at this point. Okay, so what I will do is let's look at the equations of static equilibrium. All right, let's look at the equations of static equilibrium. So we'll start off with the sum of the forces in the x direction. Okay, and basically what I'm going to have is I'm going to have negative 0.6 TAB plus 0.3243 TAC plus 0 TAD equals 0, right? Is that correct? So we'll call this my equation 1. How about summing forces in the y direction? So we have, let's see, negative 0.8 TAB minus 0.7568 TAC minus 0.8615 TAD, but then plus 800 newtons is 0. And based on the way that I organize my expressions in matrix notation, I want all these standalone terms to be on the other side of the equation. So I'm going to take the 800 newtons and move it over there. But if I do that, I have to subtract 800 newtons from both sides. So I'm going to have negative this I'm going to have that. And so that's going to be equation 2. And I'm going to scroll up and down a little bit. Okay, so that first term is 0. So if I sum forces in the z direction, so that was 0 plus 0.5676 TAC minus 0.5077 TAD, and that's 0. Okay. Sound good? So this is our system. So let me stop for a second. Is everybody caught? Do you need a second? Am I okay to scroll down up to here? Or y'all got up this? Okay. So here's our system. So all we have to do is solve that system. So we'll solve that system, and I'll say in matrix form. So all I'm going to do is take these coefficients and write them in a tabular format. So negative 0.6, negative 0.8, and 0. And then 0.3243, negative 0.7568, 0.5676, and then 0, negative 0.8615, negative 0.5077. Again, I think that the hardest part of this phase of the problem is just all the bookkeeping, keeping your pluses and minuses, straight and all that. Here's our unknowns. And here's our known quantities. 0. Here's that. So again, I posted to Teams the instructions for a number of different calculators and whatnot. Again, in the Casio, what you're going to do is, so I'll just do this part in blue. So we go to mode. We go to option 5 for equation solver, but then we're going to do 2. And then we're just going to enter these values. Make sure that you're cognizant of your pluses and minuses. So you should be entering in these quantities. And what it should yield is, hold on, I'll do this in blue, is a system of solutions, or a solution for these systems. And it should be X, Y, and Z. So I'm going to give everybody a sec. I want to see if you can go through this. Tell me what you're getting for this system. I will say to 2 decimal places just to kind of round it out. Your answer might vary a little bit depending upon how many decimals you put in here, or if you just put in the raw values. Like instead of, 7568, what if you put, 5.6 over 7.4, because that's what that fraction initially was. And notice how the calculator doesn't understand which one's X, which one's Y, and which one's Z, but we've done it in alphabetical order. So whatever X is, that's going to be that. Whatever Y is, it's going to be that. Whatever Z is, it's going to be that. Anybody have some values for me?
X is 200.53.
Okay, X is 200.5. Okay, what about Y?
371.0.
And then Z?
14.8.
414.8. That's pretty close to what I got. That's actually really close. I got like 200.91, 371.69, and then 415.53. But I had also taken these out to further decimal places. So you should probably be right around that. I know I said 2 decimal places, but actually let's go ahead. What it was 200.5 what? Oh, did I
It's 200.53.
3?
And 371.01.
And this one was 414.78.
78.
Okay. So yeah, so your X value should be somewhere around 200.5, 200.6, 0.7. This one probably in the 371s. This one somewhere between 414 and 415. I think it depends on just the amount of rounding that you have. Do I have seconds on this? Okay, good. Does anybody have any questions on just the solution process? All right, so there you go. There's our answer. So what do we have to do to keep the house from floating away? We need to have 3 cables that have a tension of 200.53. What are the units for that? Newtons. There we go. Make sure everybody's awake. TAC, 371.01. TAD, there you go. I have a couple more things to say about exam land after this, but I want to stop for a second, see if anybody has any questions. Any questions on this? Okay, all right. Any other questions? All right, so a couple of things, because I know some folks are probably thinking this in the back of their heads, so I'll go ahead and address it now. First off, from here on out, that is it for material covered on exam 1. Everything from here on out on forward is on future exams. Now, I'm sure some of you are thinking, this is a long problem, right? That's a long problem. If he's going to give us like 4 or 5 of these on the exam and only give us 50 minutes to do it, that's a lot on the first exam. The short answer is relax. You're not going to have that length of an exam. When I build an exam, I literally build the exam and then I do it and I apply a rule of 3. So what that means is if I could do the exam, let's say in 15 minutes, you should be able to do it in 45 minutes. Okay. So for problems like this, I might give you some, let's say, intermediate values to make the calculations a little faster. So the last thing I will do is give you an exam that's a time crunch, so don't worry about that, okay? I want to make sure that I never felt that it was a valuable exam experience if it was more of a test of how quickly you could hit buttons on the calculator and how quickly you could write numbers down. I don't find that to be a valuable exam. So, that's okay. That's okay. Any questions? Okay, so we are probably going to end class a little early today, but I'll tell you what we're going to talk about next time. Have any of you had any experience with cross products before? Okay, so we're going to talk a little. Some of you have, some of you haven't. What we're going to do next time is we're going to start to introduce a new concept in the class, and I want to explain why. Everything we've been doing up until now will work great, and we'll have applications in the land of engineering, provided that all of the forces all meet at a common point. The problem is that doesn't always happen, okay? So how do you handle forces that don't meet at a common point? What if you have a system where you've got forces this way, and this way, and this way, and this way, and this way? And in order to do that, we have to introduce a new concept called a moment, okay? So if forces deal with, are meant to handle situations where the forces all meet at a common point, moments handle or how we handle non-concurrent force systems. And in order to do that, we have to multiply vectors. We talk about adding vectors, but we need to multiply them. We have 2 ways of multiplying vectors, and the first and most important is a cross product, and I'm going to show you what a cross product is on Friday. But I'm going to give you a little bit of your life back. I'm going to pull up the QR code, but that's all I've got. I will see you all on Friday.